Okay, so on Monday, we looked at the product rule. We looked at the fact that you use the product rule in situations where you have something like y is equal to, let's say, x squared plus 6x minus 3 times, let's say x plus 4, just to keep it simple. And it made a comment that, really you could just multiply this out, couldn't you? And get a long polynomial and just take and use the power rule on every term, and ta-da, you're done. And you're absolutely right. It will work for stuff like that. But in section 1.7, we're going to wind up with a chain rule, which is going to allow us to do other things like, what if the problem now looked like the cube root of that first portion times the x plus 4? Well, you can't exactly multiply that out now, can you? And you're stuck, and you've got to find some other way to get this done. What if we had something like y is equal to x cubed minus 9x plus 5 to the 47th power times 3x minus 8? I don't think you'd really want to multiply that out, would you? I mean, just doing that x cubed minus 9x plus 5 should be plus 5. There's a plus missing there. Okay? Just raising that to the 47th power would be a little on the ugly side. So between the product rule and one of the next rules we're going to get to, the chain rule, you'll be able to basically look at that and write down the answer, which is incredible. It's kind of amazing the stuff that you can get done with a couple of these shortcut rules. Now, one of the things to be mindful of is with the product rule, we started it off by using that definition of a derivative, didn't we? The f of x plus h, and we subtracted a term and then added it and broke things up and did some mathematical razzle-dazzle, and ta-da, we eventually got to the formula. I did that because that's the easiest of them to see that you can really do this stuff. It all depends on that definition of a derivative. Everything we're going to do falls back to that definition of a derivative. It's just that a lot of times you won't be seeing it directly because you'll know what the rules are and you won't have to rederive them every time. Okay? For the quotient rule, I'm not going to bother deriving it for you. I'm just going to say, ta-da, here it is. We could do a similar maneuver to what we did with the product rule and work it out if we had the time. Okay? But to save time, because it'd take about half a class, what we're going to do is we're just going to say, look, the quotient rule is the following rule. Okay, so for the quotient rule, quotient means there's some division going on there. Aha, thank you, Riley. Okay, there's some division going on there. So let's say if y is equal to one function divided by another function. And we'll do some examples of this, okay? Then y prime is going to be f prime times g. Be careful, it's minus. In the product rule, you add them. With the quotient rule, you subtract. F g prime divided by whatever g is squared. And we're going to assume that g of x is not 0. Why can't g of x be 0? Yeah, you can't divide by 0, it's undefined, all that other good stuff, however you want to say it. Lots of ways to say it, but basically, you can't have a 0 in the denominator. So that's the fine print on this one. Okay? Okay, so let's take a look at a few examples here. Let's say we have something like y is equal to 3x plus 4 divided by x squared plus 9x. There. Yeah. Aha, they're trickling in. You're right, I jumped the gun. If you want to turn in your test corrections, just go ahead and ship them on up. Thank you, sir. Yeah. Yes. Let's see here. There we go. Let's get this done. And then you can actually think about the quotient rule, right? Hey, did it make sense when you did the corrections? I'm hoping it's, oh, geez, now I get it. Or, how did I miss that? Or, you know, something. Yes, I'm hoping that's exactly what it is. And that's the whole point of doing the corrections, is for you to say, ah, okay. And I also tried to identify, did I get that? Yeah. I don't know if you noticed or not, but I also tried to identify where in the book similar problems can be found. Just in case you're thinking, oh, crap, I'm not quite sure how to do that. Okay? All right. So here we've got this function. Okay? Thank you. Before we get started, there's one value of x that will not work for this particular function. What is it? Well, let's see. That would be something that's not in the domain. That would mean, where do we get a 0 in the denominator? What value of x will give us a 0 in the denominator? 0. Because you have 0 squared plus 9 times 0. Yeah. So running in the back of my mind the whole time, I can't plug in x equals 0. Other than that, it's all fine. So you always want to keep track of what your domain is when you're working on these. The derivative is going to be, well, let's see, what's it going to be? Well, first, I need to define what f of x is. F is going to be whatever's in the numerator. So my f of x is going to be this 3x plus 4. G of x is going to be this x squared plus 9x. Everybody good so far? We're also going to need f prime of x. Well, f prime is, what's f prime going to be? 3. And we're going to need g prime, and g prime is going to be, you got it. Okay, so now we've got all the pieces that we need to plug into the quotient rule, don't we? We have f prime, we have g prime. And you're going to need all of those pieces. But the nice thing about doing them down there where I did them in orange is you're just focusing on doing your derivatives, and now we'll just focus on substituting them into the rule. Does that make sense? So just take it one chunk at a time. F prime is going to be 3. G, well, that's this x squared plus 9x. Minus, be careful, it's minus, not plus. Product rule is plus, quotient rule is minus. Then it says pick up whatever f is. Well, that's this 3x plus 4 times, it says pick up whatever g prime is. Well, that's this 2x plus 9. And it's all over whatever g is. Notice the denominator is not g prime, it's g. Go back to the original function. Well, that's going to be this x squared plus 9x, the whole thing squared. Technically, that's right. It's fine. But is it simplified? No. Now, on the quiz Friday, I'm probably going to say do not simplify, because I don't want you to be using the short period of time you have on the quiz to be doing a bunch of algebra and more algebra and more algebra. But when we actually get into chapter 2, chapter 3, and especially by the time we hit chapter 3.5, you've got to simplify this, because you're going to have to set, this is a derivative, isn't it? We're going to want to find maximums and minimums. Okay, so let's think about this for a minute here. At a maximum point, aha, here's a maximum point. What's the slope there? Well, let's see, I'll draw a tangent line there. What's the slope of the tangent line? It's a flat line, horizontal line. It's 0. Good. At a minimum, here's one. What's the slope of the tangent line at a minimum? 0. So what we're going to ultimately want to do by the time we get to section 3.5 is we're going to get a function. We want to figure out where are the high points and the low points on that function. Okay, don't miss this. This is really important. The high points and the low points occur where the slope of the tangent line is what? 0. Okay? The idea is trying to get you ready to go into multiple dimensions beyond just x, where you can't graph it anymore. You cannot see it. You cannot see the high and the low points. In the real world, you can't. So how do you find them? You take these derivatives, like what we just did. It's at the top of the screen now. To find the high and the low points, what we're ultimately going to do is to set this equal to, we want the slope to be what? At a high point or a low point? 0. We're going to set that equation equal to 0 and solve for x. That's where we're headed. So realize that what we're doing right now is just part of the story. And we're going to keep tacking on and tacking on and tacking on. It's like a book with multiple chapters. You're in chapter 2 now. It's about a 10-chapter book. Great. I was hoping it was a 2-chapter book, Chuck. Nope. Okay. So realize where we are ultimately heading is to set this equal to 0, solve for x, and then that's the start of the problem on how do we make a decision. Does that make sense where we're heading? Because ultimately we're going to need to solve where does this equal 0, what we're going to want to do now is to take and get into the habit, you won't have to do it Friday, but get into the habit of simplifying this stuff. Not going to worry too much about the denominator. We've got this x squared plus 9x squared. The reason I'm not going to worry too much about the denominator is because can this function equal 0 if the denominator is 0? No, what we really want to set equal to 0 is the numerator. That means we got to clean up that numerator because we got to set that equal to 0 down the road in chapter 5 or 6, wherever it is. Okay? Well, okay, so to do that, I'm going to go back up to the equation I have at the top of the screen, and I'm going to distribute the 3, which is going to give us 3x squared plus 27x minus, now I'm going to put some brackets here because we got a chunk of work to do on this second part. To multiply that second part, we have to FOIL it, don't we? Okay, so we're going to take the 3x times each of those and the 4 times each of those. And what that's going to give us is, it looks like about 6x squared plus 27x. Now, I'm going to take the 4 times each of the things in the second factor plus 8x plus 36. Does that make sense? Okay. So what this is going to give us then is y prime is going to be equal to, well, the denominator is going to stay the same. Not going to worry too much about that, except keep remembering x cannot be 0. And what we're going to have is a 3x squared plus 27x. The part that's in brackets, I'm going to do 2 things at once. I want you to get in the habit of doing a couple things at a time because it cuts in half the amount of writing you have to do. And it's a lot of writing. Okay? So, we're going to distribute the negative, and we're going to have a minus 6x squared. Notice we have a 27x plus 8x gives you 35x, and then we're going to multiply it by the negative, so it's going to be a minus 35x. Then we have the minus the 36. Is everybody good? Okay, so it's time to combine like terms. The derivative is going to be, well, the denominator is going to stay the same. It's going to be this x squared plus 9x squared. Now, let's keep track of our bookkeeping. We have a 3x squared minus 6x squared. That's a minus 3x squared. We have, there we go, we have this 27x here minus 35x. Uh-oh. 27 minus 35, negative 8x. Okay, so I got this 3x squared accounted for, the 6x is taken care of, the 27x, 35, all we need now is this minus 36. Are you with me? When we get to chapter 5, we'll get to this, then we will take the numerator, the minus 3x squared minus 8x minus 36, and set it equal to what? 0. Don't mess around trying to factor it, because on your calculator, what do you have programmed in? The quadratic formula. Then you're going to drop back to plug this into the quadratic formula. It'll give you your answers. Good grief, that stuff that we learned back in the review chapter, still got to know that stuff, don't I? Yeah, you do. And notice all the stuff that we did earlier that was the whole problem, now it's just going to be a small part of a bigger problem, isn't it? So all that stuff that you've learned in the past, don't forget it. You've got to know it, you've got to be quick at it, because now it's not the problem, it's the next step. It's like 3 plus 4. You can't spend 10 minutes on 3 plus 4. Unfortunately, you don't. Does that make sense? Okay? I'm not trying to scare you. I'm trying to get you ready for what's ahead. Now, one of the things I want you to notice as well here, in this problem, was the bulk of the time spent on calculus or algebra? The algebra, wasn't it? The orange, the calculus there, that was real easy. Plugging it into the quotient rule, let's just plug it in. It's all the algebra you have to slog through. And be careful with it. One little mistake in that messes up the rest of the problem, doesn't it? Okay? Not trying to scare you. Just trying to point out things that you need to be aware of. Let's do another example here. Let's see here. Sometimes people are thinking, well, really, where would you ever get a fraction, a rational function, in the real world? Okay? So what I'm going to look at here is on page 161 in your book. It's just a real quick, simple example. So this is going to be example number 5 on page 161. So if you want to go back and take a look at it. And what it says is, you've got a greenhouse where the cost to grow geraniums or something or other is equal to 200 plus 100 times the 4th root of x. Oh crud, that's section R.5 again, isn't it? Those exponent things. Okay. Now, this is our cost function. X is in terms of hundreds of plants. They say geraniums, but plants is easier to write. Okay? The revenue function, R of x, is given in this problem to be 120 plus 90, that was a little sloppy, 90 times the square root of x. At the end of the day, running this business, yes, this is a greenhouse. You may never run a greenhouse. So whatever you're going to be running or involved with, substitute that for greenhouse. What you're really concerned about is profit, aren't you? If it costs you $10,000 today to operate the business, but your profit was $2 million, are you really going to worry about that $10,000? No. So the cost is something you have to keep an eye on, but you have to keep that in mind relative to what is the profit. You've got to spend money to make money. That's just part of doing business. Okay? Question here might be something like, what is the average cost? Or tell you what, the average profit. Well, if we're dealing with average profit, that means we need to, let's see, what's the formula for profit again? Revenue minus cost, and Long's back there mouth, and oh geez, that again. Okay? If you want average profit, you want to do average revenue minus average cost. Does that make sense? Okay? So what is the average profit? So the profit, and I'm going to put a subscript average, is equal to the revenue average minus the cost average. How do you compute an average? You buy a 12-pack of pop for $7. On average, how much did each can cost you? You divide by the 12. Oh, you divide by the number of items you have. Okay. So, first off, let's do what the average revenue is. That's going to be whatever our revenue function was. That's his 120 plus 90 square root of x. Kind of got a hiccup there. It looks more like a times than a plus. Now, that's the revenue function. To make it average revenue, we're going to divide by how many plants are we talking about. Now remember, if x turns out to be 1.7, that's 170 plants, isn't it? Because whatever it is, we got to multiply by 100 in the end. Cost, the average cost. Is going to be whatever that cost function was. Well, that's this 200 plus the 100 times the fourth root of x, all divided by x. Are you good so far? No big surprises here? Okay, but what we're asked to do is to compute the average profit. Well, that's the revenue, so that's going to be the 120 plus the 90 square root of x, all divided by x, minus the cost, well, that's just 200, plus 100 times the fourth root of x, all over x. And the good news here is, do both terms have the same denominator? Yeah. So we don't have to mess with getting a common denominator, do we? We're all good. So what we can do now, equals. Well, I don't know what's going to happen in the numerator, but I know the denominator is going to be x. Let's start going through this. We have 120 in the first fraction, minus 200 in the second one. So that's going to give us a negative 80, isn't it? So when you combine those two, we're going to get a negative 80. We have 90 times the square root of x in the first one. Do we have any square root of x in the second one? No. So we're going to have plus 90. Now I'm thinking down the road, and I'm thinking we're going to have to do some derivatives here somewhere. The square root of x is x to the 1/2 power. So I'm starting to move in the direction of setting up for what might be next. Then, let's inventory what we've done. We've accounted for this 120, the 200. Let's see if we can get a straight line there. We've accounted for the 90, square root of x. Aha! We still have minus 100 x to the what power? 1/4. Okay, if all we need to do is figure out what is the average profit. Now remember, this x is in terms per 100 plants. So if we put in x is 3, that would say when we have 300 plants, the average is, and you just plug in 3. Does that make sense? Now you got to be really careful, because on a problem, it might ask you something like compute the average profit when 600 plants are sold. Be really careful. A lot of people are tempted to plug 600 into that equation. But you don't plug in 600. What do you plug in? 6. Watch the units. Be really careful on the units. It could make the difference between having a profit of $1 and $1 million. It's all the same. Watch your units. Okay? Okay, real fair question. And this is where our derivatives come into play. Remember, a derivative talks about a slope. It talks about how are things changing if I'm here and I take one step. The line that connects those 2 points tells me how fast are things going up. That's what the slope does. It tells me how fast is stuff going up, doesn't it? Does that make sense? So, a real fair question would be something like this. Determine the rate of change in the average profit when, and I'm going to say something like x equals 6. Or, realistically, if you're working in a greenhouse, when you are considering increasing production from 600 to 700 plants. This is the way it would actually be, or something like this is the way that they would be saying it when you're talking to folks there, talking about the operation of the greenhouse. Now, here's where you're going to earn your money. You need to hear that, but realize we're talking about a changing rate. A changing rate means a derivative. And where is the start point for our change? The 600. You need to be able to realize, one, we're talking about a changing rate. That means a derivative. You need to realize what is the starting point. A lot of people want to plug in the 700. That's not where you're starting. Remember, you've got 2 points, and you're starting at this one. Okay, so you need the slope there to tell you what direction are we headed to get to the next one. Does that make sense? We need the slope at 6 to tell us where are we heading. Well, what this really is asking us to do, and lots of folks in the greenhouse aren't going to hear it this way, this is what you need to hear. What we really need to do is to compute the derivative of the average profit and evaluate it at 6. Now, the other folks in the greenhouse, they have all kinds of good information. How do we control bugs? How do we deal with fertilization of the plants, not over-fertilize them, kill them, or not give them enough? How much do they get water? How much light? I mean, there's all kinds of stuff going on, right? Your big song and dance is here, we need to do this derivative. Well, let's see. The function we're dealing with is at the top of the screen. If we put 6 into that function at the top of the screen, what value are you going to get back? I don't mean number-wise, but what's the number going to mean? Making it up, suppose it's 17. What's 17 mean? Okay, that's the profit, the average profit you're going to make at whatever number went in. Okay, so the average profit's going to be 17 at, let's say you put in 2. If you're producing 200 plants, the average profit per 100 plants is going to be 17 bucks. Does that make sense? Okay, better be more than that or you're not going to be in business long, right? Or don't need to carry that product. Okay, let's take a look at this. First off, we got to compute the derivative, don't we? Well, we're going to use that same rule that we just talked about for the quotient rule because it is a quotient. Easy part, what goes in the denominator? X squared. Aha! Well, that's easy enough. X squared. Okay, I'm thinking in my head, X cannot have a value of 0. But if you're making 0 plants, what's your profit? It's going to be negative actually, isn't it? Because you're still losing on paying for the greenhouse, paying for the people, everything else. Your profit is going to be negative. It is possible to have a negative profit. Ooh, that's not good. Okay, so we've got that part done. Now, what goes in the numerator? Well, it's going to be f prime times g minus f times g prime. You may need to look at, but you got it there in your notes. F prime. That says take the derivative of this puppy right here. When we take the derivative of that term by term by term, the derivative of negative 80 is 0. That was easy. That's gone. The derivative of 90x to the 1/2 power. Way to go. And where did 45 come from? I thought it was 90. Oh yeah, you multiply the 90 times the half, and half of 90 is 45. X to the, be careful, it's a negative 1/2. The next one, minus 25. Good. Does that make sense where that came from? Now, sometimes people will make it through there and say, that's got to be enough. I got to be done. No, we still got to multiply this by x, which is the g term. Then we're going to have minus. Now we're going to have f. Well, that's what's circled in yellow. I'm going to get rid of that circle so you can see it a little bit better. It's going to be this minus 80 plus 90 x to the 1/2 power minus 100 x to the 1/4 power. That's just f. Then we need to multiply that by g prime. But what's g prime? It's 1, isn't it? Okay. If we were going to doodle a lot with this, you would probably want to try and simplify it. My thought is, all I need to do is plug 6 in, true? And get a number out of it. Does that look like something you'd want to do in your head? Yeah, me neither. So what's going to wind up happening here, it's time for the calculator. So P prime evaluated at 6 is going to be this 45 times 6 to the negative 0.5. Why did I put negative 0.5 in there? That's the decimal version, and it's time to whip out the calculator, right? And are you safer plugging in a decimal or trying to include a whole fraction? The decimal's safer. Okay, minus 25 times 6 to the negative 0. What's that going to be as a decimal? 7.5. Great. Now it's this whole thing here times x. That's going to be times 6. Minus. We have a negative 80 plus 90 times. We could, if you wanted to, since I'm thinking about the calculator, we could just do this as the square root of 6 because you got a square root button on your calculator. Okay? Then we're going to have minus 100 x to the 0. Not x. It's going to be 6. It's going to be times 6 to the 0.25 times 1, or you can just ignore the 1, over what? 36, 6 squared. Oh yeah, that looks like fun. Are you good? Notice on this problem, comparatively speaking, did the derivative the calculus take a lot of time, or is it just one quick step? It's one quick step, isn't it? The only thing here that was calculus was that. All this stuff up here is algebra. All this stuff down here is algebra. Now, I'm not going to spend the time to actually plug that in. I'm assuming that you can do that okay. Take your time with it. Pay attention to the parentheses, okay? And you'll get through it. Now, suppose P prime of 6 equals, and I am just making this up. I have no idea what the actual value is. I'm making it up. I'm just making up some number. Let's say 175. What does that mean? How do you put that back in words? Yes, you could walk up to the other folks at the greenhouse and say, hey, P prime of 6 is 175. And the horticulturists and folks like that, they're good. They're well trained. They know what they're doing. They got any idea what P prime of 6 equals 175 is telling them on a business decision? No. That's your job. You have to be a translator. Actually, you got to learn to speak 2 languages, or at least 2. Okay? One of them English, the other one math. And you've got to hear the problem that they're explaining in English, convert it to math, get a number in math, and convert it back to English. So you're really learning a foreign language. Or another language. Okay? What does this mean? Now remember, it's a derivative. Okay? And if you go back to the earlier parts, the average was talking about, well, let's see, the denominator is x, that's 100 plants, isn't it? So whatever we're saying, it's going to be per 100 plants. Okay. What's the other part of revenue? Isn't that money? Okay. And in this case, it's going to be US dollars. Okay. What this actually says is, if we increase production, from 600 to 700 plants, okay, and you got to identify that first, because this tells you, what are we talking about doing? Are we talking about going from no plants to 100 plants? From 10,000 plants to 10,100 plants? You got to know where we're talking about the changes taking place, because the profit is going to behave differently at different locations. If we increase production from 600 to 700 plants, the profit will increase. How do we know it's increasing? It's a positive number. By $175 per, is it per plant? Or what's X in terms of? 100, isn't it? So it's whatever the units are on X, it's going to be per 100 plants. Now that's not the revenue, that's the profit. Okay, and keep in mind, revenue is very different from profit. You can have a lot of revenue. Ha! Today I took in $50 million. Really? What'd you do? Well, I sold an F-35 fighter plane. $50 million, is that really going to cover the cost? Not hardly. So even though, whoa, my revenue was $50 million, I forget what they cost. I haven't bought one recently. But just making up something that, a B-2 bomber, there we go. That's one that'll cost you a chunk of change. Okay? If I sell them for $50 million a piece, am I in trouble? Yeah, because those things cost way more than $50 million a piece. So just looking at the revenue doesn't really tell the whole story. The profit does, or it gives you a different view of it. Does this make sense? This sentence here is a real good pattern to use for the answer to every single question we're going to do later on when it comes time to interpret the numbers. The pattern is, if we increase production from, and then whatever your start number was, to whatever the next unit is. And remember, we were dealing in units of 100 this time, weren't we? 100 plants at a time. So going from 6 to 7 really means we're going from making 600 plants to 700 plants. So you always want to put your disclaimer in first. If we're going to go from 600 to 700, then the profit will, and whatever it is, increase or decrease by, there's our number, the 175 per, and the 100 plants came from, what are the units on X? There's a whole lot of wrapping that goes around that 175, isn't there? But that wrapping is important to make sense out of what it's telling you. Are you okay with that? Now, you may need to go back and listen to this video again a time or two to figure this out, because seeing and hearing that once, oftentimes, well, I'm not quite sure that took. And that's fine. That doesn't mean you're bad and you're awful and you're dumb. It means this stuff's getting more challenging. You're having to wake up a few more brain cells to get this working. Okay? Does this make sense? Does this look like something a business would actually need information on before moving forward? Yeah, do we increase production? What if that would have been negative? What would you tell them? No, don't increase production. Because there comes a point in any situation where if you're already at the maximum profit, if you move further, what's the profit going to do? It's going to decrease. If you are at the optimal profit, moving in either direction is going to be a decrease in profit. Okay? And we're going to learn, how do you figure out what that optimal point is? How do you figure out what the optimal price is? How do you figure out what the optimal number sold is? All kinds of stuff like that. Are you good? Okay, so this is all wrapped around quotient rule. Okay, quotient rule is up here somewhere. There it is. There's the quotient rule. Make sure that you know it. Can't do any average profits, costs, or revenue without the quotient rule, can you? And those are actually rather important in business. All right, that has section 1.6 done. Yahoo, you survived it. Let's jump into section 1.7. So is the shuttle running late, or was it surviving driving on the expressways?
Driving on the highway.
And other people weren't. Well, I'm glad you made it safe and sound. Section 1.7. There are basically 4 rules for derivatives that you need to know. Power rule, product rule, just got the quotient rule. There's only one more to go, and you've got them all. You've got all the tools you'll need in your toolbox. It's what's called the chain rule. Just like with the product rule, we could go through the definition of a derivative and do all the mumbo jumbo that it takes to get to what's going to happen here. Okay? But instead, we're just going to take a shortcut. Okay? So, if y is equal to f of g of x. Now, this is going to look like a swarm of killer letters coming at you. Okay, but we're going to come back and we're going to talk about this. Then y prime is equal to f prime of g of x times g prime of x. Oh yeah, that makes perfect sense, Chuck. What on earth are we talking about here? First, notice that g is inside of f of x, isn't it? This means we're going to be working with a composite function. What does a composite function look like? Okay? Composite just means several things put together. So for example, let's say I have something like y is equal to the square root of 3x plus 7. There's a function on the outside, the square root. And inside of that, there's another function, 3x plus 7. This is a composite function. It's made up of 2 pieces. You have the linear function, 3x plus 7, the line. Inside of another thing, the square root. Does that make sense? So it has 2 pieces to it. Okay? Kind of like I've got the backpack. That's the outside function. But inside of the backpack, hopefully, aha, here it is, my calculator. So it's a composite function with the calculator inside of the backpack. Same idea there. Now, what's going to wind up happening for something like this, we can rewrite this as y is equal to this 3x plus 7. Don't stop. Crutter doodles. That's nice. It stopped writing. Okay, so it's going to be, technology is wonderful. It's going to be y equals this 3x plus 7, and that whole thing has a square root applied to it, doesn't it? What is the exponent that means square root? 1/2. When we do the derivative, notice it first says f prime of g of x. What that actually means, this first part of the notation, f prime of g of x, that says take the derivative of the outside and leave the inside stuff alone. See it? The g of x is still, it's the inside stuff. Nothing happened to it, did it? So what I'm going to do here is I'm going to first put down the inside stuff. There. It didn't change. And on the outside stuff, I'm going to take the derivative. Well, to take the derivative with this 1/2 power means I'm going to bring the exponent out front, and it's going to become a coefficient of 1/2. And the exponent is going to decrease by 1, so this is going to be to the negative 1/2. There's the derivative of the outside part with the inside left alone. Does that make sense? Once you have that done, now we're going to do what? The derivative of the inside. And the derivative of the inside is 3. To make this a little bit safer, I'm going to write this as 3/2 times this 3x plus 7 to the negative 1/2 power. There's the derivative. Are you okay with that? Maybe. Okay. So for Friday, let's see if I can get this thing to continue writing at some point here. For Friday, what's going to be on the quiz? The quiz is going to be product rule, quotient rule. Those are in section, what was that, 1.6? I'm going to throw some simple chain rule on. We're going to talk more about the chain rule. Section 1.7. You can dive in and start trying the homework in section 1.7 as well. But the 1.6 homework, I'm hoping you already did the part with the product rule. So now all you need to do is go back and do the stuff with the derivatives. And that'll get that taken care of for you. Then in 1.7, start some of the simpler looking things with chain rule. And we'll do a little bit more work with chain rule. What am I going to check in the way of homework on Friday? 1.5, 1.6. Hey, is this power rule stuff ever going away? No, in fact, when we did the derivative of the inside, how did you do the derivative of 3x plus 7? That was power rule, isn't it? It's kind of like adding and subtracting. They're never going away. The earlier rules, they're never going away. Folks, I hope you have a terrific day. Safe trip home, and I'll see you on Friday.